Uh, Good afternoon. Our project is over the HUZ, and our team name is Platinum Team. Motivation slash features. The need for advanced verification techniques is highlighted by hardware vulnerabilities such as Spectre and Meltdown, as conventional methods are unable to um, address the problem of increasingly complicated processor designs. Our enhancement to the HUZ will introduce timing-based coverage metrics aimed at finding reduced instruction set computer 5 processor vulnerabilities caused by timing gaps. The HUZ dynamically generates test inputs that repeatedly mutate over time through untested hardware paths and find subtle vulnerabilities. These improvements will enable better coverage of processor logic and advanced hardware fuzzing methodologies to ensure robust security for processors.
This is the background section of our report. Key terminologies. This is pretty much where we lay the groundwork for understanding hardware verification. Design verification ensures that a hardware design meets its intended specifications. And we explored its two primary methods, dynamic and formal. Dynamic verification uses real-world test inputs to validate design behavior as it executes, while formal verification employs mathematical models to confirm correctness across a range of scenarios. Each of these methods offer strengths, but also, of course, face limitations, particularly in handling scalability and the complexity of state spaces. These limitations, as highlighted in our report and research, emphasize the need for a more dynamic and adaptive technique. Fuzzing, with its ability to generate random or semi-random inputs to explore untested pathways, kind of stood out as a method to address these gaps. By integrating fuzzing into our approach, we aimed not only to extend coverage, but also to uncover vulnerabilities more effectively. So these insights informed our use of the HUZ to target the unique challenges of the RISC-V processors and pretty much laid the foundation for the project's focus on enhancing hardware verification techniques. Next is software fuzzing on hardware, where we explored the challenges of adapting software fuzzing methods to hardware testing. Software fuzzing, like the widely used AFL, detects vulnerabilities by pushing software systems into unexpected states. However, as noted in our report, applying these techniques to hardware presents critical challenges. Hardware tends to operate with inherent parallelisms and precise timing dependency factors that traditional software fuzzers designed for sequential execution and crash detection struggle to handle. So tools like RFuzz showcase initial promise by essentially converting hardware descriptions into intermediate models, but we're unable to detect deeper hardware-specific issues like timing glitches or state transitions. These gaps reinforce the need for a more tailored approach, one that could address the intricacies of hardware systems. This recognition pretty much influenced the direction of our project, underscoring the importance of adapting fuzzing techniques specifically for hardware environments to ensure comprehensive testing. Next is converting hardware into software, which examines how tools like Veriladder translate hardware designs into equivalent software models for testing. This approach allows hardware to be simulated in a controlled environment, usually enabling basic functionality testing and easy integration into existing software workflows. However, as also highlighted in our report, this method has limitations when applied to complex hardware systems. Usually, timing related bugs and the parallel execution inherent in hardware are not effectively captured in software models, making this pretty difficult to identify nuance issues. So, these shortcomings emphasize the limitations of software centric methods in fully addressing hardware vulnerabilities. The broader theme being pretty much the importance of aligning testing methodologies with the unique characteristics of hardware, right? So, this context is what solidifies our focus on direct hardware fuzzing, as it offered a way to explore these complex intricacies more effectively and sort of bridge the gap left by software simulations. Lastly is hardware fuzzing on hardware, which focuses on the HUZ. which is pretty much the tool at the center of our project. Unlike methods that adapt software fuzzing tools or convert hardware into software models, the HUS directly test hardware designs with inputs that mimic real world conditions. This direct approach allows for the exploration of critical areas of hardware functionality that other methods could not fully address. By continuously iterating, generating, and mutating inputs, the HUS is able to target vulnerabilities such as timing issues, finite state machine errors, and side channel attacks, all of which are unique to hardware. While these capabilities were informed by the success of software fuzzing, the HUS was designed to overcome its limitations, focusing on hardware's parallelisms and timing dependencies. So this signified the potential of hardware-specific fuzzing techniques, not just to enhance coverage, but also to uncover vulnerabilities that might have otherwise remained hidden. And I mean, ultimately, this further validated the importance of tailoring testing methods to match the distinct challenges of the RISC-V processors.
So here is the initial setup we've done. So the first thing is to create a project folder on the Olympus server and load the necessary files using this command line, and you copy the further set of files using this command line. So we've made some modifications to the housinstall.sh. The first thing is to do is basically update the folder path in line 1 to the projects folder and comment out lines 21 to 27 for the initial setup. And you run the script. And the next one is to uncomment lines 21 to 27 and comment out lines 16, 6 to 15 and run the script again. And you add a couple of letters, which is basically over here. You add an R to lines 105 and 116 so that the code actually reads it properly and runs it. And the validation is basically we run the script again after doing all these changes, and you can see that 3 files have been should be created in your mobile XTherm server, and I can just show it to you real quick. This was the final screenshot we've taken after setting up the HUS. I can show you the files which were created. So if I go to the mobile XTherm and I run this part, it's going to set up. It's going to say setup is complete. I'm going to stop this in between because it's going to take a couple of seconds to run. And to show you the files which have been created, I'm going to go to actually open this up. It's going to show the respective benchmark and the test cases. And yeah, this is about it.
Okay, so for the initial results of the HUS, what we found was that the benchmark data shows good initial coverage metrics, but one of the areas we found that could be improved was timing analysis. So what we see below here is figures 3 and 4, the initial coverage that we were able to achieve for the RC and boom processors. The RC processor had 32.55% coverage and average runtime of just under 5 seconds. The boom processor was slightly more effective with 37.77% coverage and also just under 5 seconds of runtime. And the challenge that we found was that the coverage metrics do not account for timing discrepancies in the test case execution. And our solution, the improved results that you'll be seeing in the demo in the following video, is that we implemented a modification, SimProg, to measure the time taken for each test case simulation. Our initial approach was to flag the test cases with longer execution times as the potential bugs. And one of the issues we ran into with our initial approach was that many of these flagged cases were not bugs, but valid variations in the instruction execution, such as load store or add sub. So our second approach was to calculate the average execution time across the test cases and only flag the cases that deviate significantly from the average. And after doing this, you can see the results in figure 5, which is the time taken for each of the SimProgs to run.
As for the code part of it, so the code we modified is the simproc function, which is under the proxim.py file. First thing we have to do is import time because we are dealing with the time commands. And then under the simproc function, what we did is first we started to measure the initial time, which is just the current time for the program, and then the simulation is run. This part of the code is where the instruction is taken from the instruction dataset and then run in the simulation to simulate a processor, here the RISC-V processor. And then we measure the end time, which is just the time per instruction, which is the current time minus the initial time before the simulation. And then we print it out to the command line to see what time the instructions are taking basically. And each time it's different because different instructions need different number of clock cycles to run. And then the thresholds are basically here, minimum time and maximum time are some X number of clock cycles the instruction is supposed to take. Like for example, loads and stores take more clock cycles versus like just adds or subtract take less clock cycles. But like these thresholds would be changed based on the average time instructions take. And then the flagging logic hence would be if time per instruction is more than the maximum time, or if time per instruction is less than the minimum time, we do a print statement. So here it's just a print statement, but this print statement should be replaced by a logic where this current, like this simulation is tagged to basically saying it's a potential bug. I'll just run my code and show it to you. So this is the setup code. And then what the modification we made is this printing out to the command line basically. And then as you can see, for each instruction, the time taken is different because the instructions are themselves are different. And then the coverage metrics are also represented. This is for the RC benchmark and this is for the boom benchmark.